very, very, very much. First off, I can't tell you how honored and how humbled I am to have been asked to come back to KU and talk. And actually, the first thing I want to do is to introduce my wife, Jeannie, who came up with me today. When she learned that I was coming back to the KU campus, she figured some adult supervision and moral leadership was necessary, so she came back with me to make sure all those squares were filled. So Jeannie is here with me, and I'm really glad. I'm very happy. Now, I'm going to really be relying on Leslie to operate these things. 185 different kinds of airplanes. The Air Force is still trying to find one that I can handle okay. This may be 186, I'm sure. Guys, when I say guys, I mean guys and gals, obviously, but I'm going to really, really buzz through this. I kind of apologize. I brought the whole load of hay for you, and I didn't know for sure how much time we had. We don't have a whole lot of time. We got about 45 minutes, but I'm going to do pretty much what we've got on the agenda here. I'd like to let you know a little bit about some of the early X-15, early X-series rocket airplanes that led up to this development, this relatively rapid expansion of speed and altitude for aircraft, for winged aircraft, that happened during the 50s and 60s time frame, where that laid in with respect to the spacecraft, the Mercury and the Gemini spacecraft flights. Then I'd like to go ahead and get right into the X-15 and describe it for you a little bit. It's got some unique design features, and those of you familiar, there's a lot of you familiar with aircraft design, may find some things interesting as you're coming to the home, to the mecca of aircraft design here, and I make a comment like that. And do it. Give a hand to the teams that have I have been proud of a lot of things during my life, but very few things I'm more proud of than the record that the University of Kansas has made and the students have made in the design competition. I mean that seriously. It lets you walk around the NASA campus down there at Houston really puffed out with your KU shirt on. I'm very, very proud of you. I'd like to go through a few of the things that we learned. The key things that we learned during a re-entry, in getting above the Earth's atmosphere, beyond the sensible atmosphere, where there is no control of the vehicle other than with reaction controls, little jets for pitch, roll, and yaw, no control over your ground track at all, and transitioning back into atmospheric flight, because that was key in the confidence to press on with the space shuttle design. Some heating lessons we learned during aerodynamic heating, thermodynamic heating, and then how they applied to the space shuttle. And then the film, as I mentioned, boy, I keep pushing the wrong button there. And then I hope we have some time there for questions and answers. The early X-series airplanes, really a unique set of airplanes. There was boy, I keep doing that. The X-1 in series that we'll cover, the X-1, the D558-2, the X-1A. Now, there were a whole bunch of X-1 airplanes. There were actually I believe five or six different models, and 11 different X-1s actually built. A lot of them, after the transonic problems were essentially, after they had their arms around how to fly through the transition period, where the shock waves started to form on the airplane. Mainly then they started looking at different cockpit shapes. The bubble canopy, knife edge like the 102, the F-104 and F-100 had the bubble canopy, the knife edge like the 102 and 106 series airplanes, to see if there were any unique dynamic or heating problems that they needed to worry about for the Century series airplanes that were in the design and in the early test phase. Then the X2 and let me get my pointer here. X2 and then on through to the X-15. The objective of all these airplanes was to gather data to build better airplanes. By better, at that time it meant faster airplanes than the bad guys, because speed was the key then. They weren't really concerned or looking for altitude expansion. That kind of came as a result of having to get a little bit higher in order to get that kind of a Mach number with the thrust that you had. And so the speed was really the thing, but it really laid the groundwork for space operations with the space shuttle, which we weren't really aware of or focused on at that time. It was a little too early. The X-1 airplane started flying in 1947, and the various models of it flew through 58 actually. 558, the X-15 here. Actually, we were flying X-15 prior to the Mercury, Gemini, and Apollo spacecraft. So they happened kind of in parallel. They were competing a little bit, as a matter of fact, too. The X-1, everyone's familiar with. Chuck Yeager flew this airplane, first time to actually penetrate the speed of sound and to solve the problem of controllability of the airplane as the shock wave started to form and then formed and reduced the effectiveness of all the surface area behind it. Chuck found as he approached Mach 1 that, as he said, that to Jack Ridley, who was his flight test engineer, he and Jack were very, very close. And I remember Chuck talking to me about it. He said, I told Jack, damn airplane was getting kind of squishy out there. And this is kind of technical, I know, so if I'm getting ahead of you here. But the elevator was becoming ineffective. And what was happening, of course, the shock wave was forming on the thick part of the horizontal stabilizer, blanking out the little elevator, this little thin elevator that at the time of the design, they didn't realize that that's where the problem was going to be. Jack Ridley realized that the whole horizontal stabilizer had a tremendous trim range, and you can kind of see it, and maybe there'll be another film, I hope, a picture of it, I hope you can see, that was driven with a pneumatic motor, a little pneumatic motor on a jack screw, and that would run the elevator up and down. And Jack said, Chuck, I believe if you think you got enough control to keep ahead of the airplane, we can rig that up and put a bigger pneumatic tank in there so you can just use that switch, the trim switch, to actually fly the airplane through this transition as the shock wave is forming and moving back, and you can get through Mach 1. And they did it, and it worked. And it became a very highly secret thing, too, because they didn't want the bad guys, who at that time was the Soviet Union, to really know what the solution was to go in transition. The MiGs were having trouble with the RF-86 was having troubles with Mach shock waves forming, so they kept that a secret. But let me go through these airplanes kind of quick. The X-1, actually there were 3 aircraft were built. It had a 6,000-pound thrust engine. That was actually 4 chambers of 1,500 pounds each. And they were controlled by switches. They were on-off. You couldn't throttle them. But if you wanted to vary the thrust, you could turn on as many as you wanted, or if you wanted to decelerate a little bit, you could shut one of them down. And so you controlled your speed by shutting down or starting up these 4 engines. He got it to Mach 1 and about 72,000 feet. But again, the altitude was kind of secondary. That was an Air Force NASA program. The Navy had a joint program going with NASA that was called the D-558-2. And it was a slick-looking airplane. It had a neat, sexy pointy nose. And, whoa, I kept the wrong way. It had a very pointy nose, swept wings, a lot bigger tail surface because they realized you're going to need more directional stability on the airplane the faster you get. And just looked like a good air, and it was designed to go Mach 2. And in doing so, it got up to a little over 80,000 feet, about 83,000 feet. But it did get to Mach 2. It had the same engine in it as the X-1. It was a Navy airplane. They designate everything different than the Air Force does. So it was called this term here, but it actually was the same engine, 6,000-pound thrust, a lot more fuel. So the engine could burn longer and could accelerate for more time. They got it up to Mach 2 very successfully and flew it at that speed. The next airplane, then Chuck was livid. The Air Force didn't really like the Navy holding the speed record, so they said, what can we do real quickly? With the X-1, and Bell came back with a solution to stretch the fuselage, add more fuel, and with more fuel, they figured they could get out that far. And they had confidence. They went ahead and changed the canopy design. Didn't have anything to do with the problems that involved with the airplane. But Chuck got the airplane out to about 2.44 on a program that was an incremental expansion program to increase the velocity. He got it out to 2.44, not quite to 2.5, shut down, was ready to come back and then get ready for the next flight to take it on to 2.5. And he turned to fly back to the field, to glide back to Edwards to land, and the aileron, the outboard aileron, the yaw, from the aileron input, yawed the nose around, got it. There wasn't enough vertical fin to stabilize the airplane directionally, and it tumbled and went out of control. He tumbled actually a pretty violent tumble from 90,000 feet down to about 15,000 feet, where he finally recovered it. And he said, you know, I didn't have an ejection seat, so he said that I was going to fly the damn thing in because I couldn't get out of it. And so he got it recovered, brought it in and landed, and they figured, well, maybe that's fast enough on this airplane. The next airplane, though, was an Air Force airplane designated the X-2. It had a larger engine. It had a bigger thrust engine, 15,000 pounds. It had there were two of them built. Actually, both were eventually lost. One was lost early on in the program while it was just doing a mated test flight, and the other one then lost control. He got it out to 2.87 on that incremental expansion program. Didn't ever get to Mach 3. Had the same problem that Chuck did. Rolled the airplane to come back to the field. The outboard wing with the aileron down caused drag, drug the nose around, and yaw roll coupling got him. Mel didn't get out of this one. We lost the airplane and the pilot on this one. In doing so, he got it up to about 126,000 feet. Again, it didn't have reaction controls, so they weren't really looking to be able to control an airplane in a low dynamic pressure condition yet. They were after speed. The next airplane then in line was the X-15 in this research program progression, and this one was a pretty good bite. The X-15 had some unique characteristics. First of all, it had a 60,000 pound thrust throttleable engine. You could throttle it back to half thrust or Mach 3. We got the airplane actually to 6.7. It was designed to go. The design envelope was Mach 6 and 250,000 feet. They figured 250,000 feet, that's got to be above any sensible atmosphere, anything you guys can use with control surfaces to fly with. So that was a design goal. We actually got it up to 354,000 feet. It did have some unique features. It was made of steel, Inconel X steel, very high heat resistant surface or covering, because aluminum would melt. And in fact, the film that you're going to see is a wind tunnel model at a high Mach number with temperatures that were kind of expected at these Mach 5, Mach 6 speeds. And you see the wing melts off because the tunnel model was made out of aluminum. I don't know whether they didn't think about that yet or not. But as Neil Armstrong used to say, that's when the engineers went back, scratched their heads and said, well, maybe we better find something else to build this out of because that doesn't work too good. Let's see. So to review very quickly, the X1 was designed to go Mach 1 when it did. It got up to about 70,000. The D558 was designed to go Mach 2, and it did. Got to about 78,000, 80,000 feet. The X1A, kind of a hurry-up, kludged-up design, was they were hoping to go Mach 2.5. Didn't quite happen. Didn't work too good. Went out of control. But Chuck was able to get the airplane back. And the next one then was the X2, which was designed to go Mach 3, and that didn't work out. So these two worked okay. This one not so good. This one not good at all. So it was a pretty gutsy call on the part of the engineers and the designers and the people that work in the concepts at that time to say, okay, our next shot is going to be an X-15, and it's going to have an envelope that looks kind of like that. Mach 6, again, as I say, was Mach 6 was the design goal. Pete and I got it out to 6.7, and that didn't work very good. So we figured that better be as fast as we try it. You'll see that in the film. We'll talk about that later. Designed to go to 250,000 feet. We actually got it up to 354,000 feet. So the message on that slide is that it was a pretty aggressive, and they had to, you got to hand it to the people at that time to be ready and willing to put their careers and their reputations on the line to bite off a big envelope expansion like that. And recall all this happened with engineering and with tools available in the 1950s. Didn't have iPhones or computers or anything that had people walked around wearing slide rules. And a lot of you in this room, I'll bet you can remember here at KU, where the engineering school, where you guys would walk around with the slide rule in a leather case. You had the scabbard there. And are there any theta taus in the room here? Ah, there you go. Did you have to make a slide rule? You have to build a slide rule? Did you have to? You didn't have to, did you? God, I tell you, they used to make us build these 3-foot long slide rules, and you had to use those. How much was it? 2 weeks? You had to use it at school in class. You couldn't carry your slide rule. You had to use the slide rule you built for 2 weeks, and it worked. I mean, they worked okay, but they were hard and they were a mess to carry around. But the other things were pretty limited as well. These things you can read. I'm not going to spend a lot of time on them. The inertial systems. Just spinning gyros was all we had, and they would precess really badly under acceleration. When the engine was burning, you get up to 4 G's acceleration, the inertial system began to drift, and it was not real accurate, so you couldn't use it for shutdown, for example. So many feet per second you wanted to shut down at a certain velocity. You had to use a second hand, a sweep second hand for shutdown, and the engineers knew what the thrust was, what the accelerations would be, and they knew how many seconds of burn time it would take to get to the condition that they wanted for that particular data. Let's see, inside the airplane, mostly fuel tank, liquid oxygen, and anhydrous ammonia were the propellants. The tail had a kind of a unique feature. It's a wedge-shaped tail, and I'll talk about that a little bit later. The cockpit up here was very relatively small for a pilot. When the canopy would come down, the canopy, and you'll see this in the film too, would actually come down right around the pilot's head, so that it came down to here, and then the fuselage part of the canopy would pick up and go on around your shoulders. So you were really snuggled in there good. They strapped you in really tight so that you wouldn't flop around. There wasn't any room to flop around in there anyway, even if they didn't. But you were really strapped in a very small container. And I was 6'1" when I was in the program. I was a little bit too tall, but I learned how to slouch and how to run and compress your spine. So I was able to get in the program all right. But Scott Crossfield, who was a tremendous engineer, I mean, he was more of an engineer than he was a test pilot. He was the designer, really, of the cockpit, and he did a beautiful job. Everything was laid out right where you would want it, where you could reach it and everything. The only thing was Scott was 5'9", and there nothing adjusted. The seat didn't adjust, the rudder pedals didn't adjust, the throttle didn't adjust, nothing adjusted on the X-15, or any of the test airplanes, really, most of them anyway. And when I got in that thing, boy, I was really cramped, and I felt like my knees were up against my chest. I wasn't going to say a damn thing, though, because but it was cozy in there. I didn't have to really stretch and reach for anything, but it was kind of crowded. The cockpit looks pretty conventional. Flight instruments are pretty conventional. The only problem is some of them are pneumatic and some of them are inertial. The inertial stuff, or the pneumatic stuff, worked really good, and we had to use for gliding back in and landing the airplane, for energy, controlling energy on the way in. The inertial instruments, rate of climb, altitude, and those instruments, they didn't work too good. They drifted while the airplane was under power, while the engine was burning. But when you shut the engine down, then they would come in pretty good. They'd settle in, and they were pretty good. But so you really didn't, during a lot of the flight, you really didn't have a whole bunch to go on except looking out the window and making sure things were good, and the little sweep second hand. Now it had 3 controllers. It had a center stick like a conventional airplane. They thought at first that pilots would feel more comfortable and feel more at home with a stick in the center to land, because that's what all the airplanes had back then. They realized that during acceleration, particularly on high-speed runs where dynamic pressure builds up real high, when you shut the engine down and you go from +4x acceleration to a -1, just like that you, with a hand out there with a pressure suit and the weight of the pressure suit, you could get some rocking in the stick, some unwanted pitch inputs in. So to avoid that, they put a sidearm controller that pivoted around your wrist. So in pitch, you flew it like this, and in roll, you would actually roll it like that. Yaw were still the conventional rudder pedals. So when the engine quit, if your arm went forward like that, you were just shoving against the rotational point on the hand control, and it didn't make an unwanted input. Let me get back here. However, the sidearm controller, and these two were connected mechanically with cables, the sidearm controller and the center stick. So when you flew with this all the time and you'd move it in roll or pitch and stuff, that center stick would move back and forth. At that time it was kind of spooky because, you know, you can get things to do that now, robots and stuff like that, but that stick moving around was a little disconcerting at first. Boy, I'm just having a real hard problem with this. For the reaction controls for flight above the atmosphere, where the aerodynamic surfaces were ineffective, we had a reaction control system, a flight control system with a handle that came out as just a regular old handle that came out from the cockpit, and you can see it right here. And you'd lift up and up for nose up pitch, push down for nose down, left and right, and twist it for roll. And it activated. Hydrogen peroxide was under pressure, under helium pressure tank, and the hydrogen peroxide would be forced down to a line down to a little ball right on the backside of the instrument panel. And in the backside, it was like any of you torn apart your shower head, you know, a Delta shower head where you can lift it up and down for more water or less water and twist it for hot or cold. The same damn thing as that. And or one of them was first, and I don't know which was first, except this one had 3 axes. And when you lifted it up or down, you just opened up a port that allowed this hydrogen peroxide to flow out to the respective jet that you wanted to activate. And that peroxide would go over a silver catalyst bed, turn into steam, and that was what gave you the force to either bring the nose up or down or left or right or to roll. Very simple, but it really worked. It actually worked pretty good, except that in altitude flights, and quite frankly, I'll say it now so I don't have to say it later. At first they thought that, okay, you guys, when you're flying and you're doing these altitude flights, you're gonna pull up and climb, and the engine will shut off at about 140,000 feet, and the rest of the flight is going to be coasting up and over the top. So you're flying the airplane, and this hand is going to have to be minding and tending and taking care of and petting the rocket engine, because it was a kind of a little feisty thing itself. So you wanted to keep this hand over here, and so you control it. 240,000, they said, that's probably about where you're going to quit flying with aerodynamic surfaces, and you're going to have to go to reaction controls. So you just quit flying with the right hand, with the rotational hand controller. You'll go over to the RCS controller, reaction control system controller, and fly it. Fly it up over the top, and as you're coming back in, probably about 140,000, then you can quit flying with this one and go back and flying with the aerodynamic surfaces to come on in and land. And we'll find that out by incrementally increasing the altitude and seeing if that was the right altitude, but use that for a gauge. Well, it turned out that wasn't right at all. It's a very subtle transition from aerodynamic surface to reaction controls, particularly on reentry. And we found a lot of times that with the pressure suit on, and it would inflate a little bit at altitude, your arm would get pulled in a little bit. So without knowing that, you were putting in a little aileron as you were coming back in, and we would correct that. It'd just roll off a little bit as you're coming in. We'd correct that by saying, well, guys didn't quite get it rigged right this flight, so we'd come in with reaction controls and bring the wing back up and correct and bring it, until you got into where the aerodynamics got pretty effective. But by then you were flying with the right-hand controller anyway, so it didn't make any difference. The only thing was we were running out of fuel in hydrogen peroxide, and of course we'd sit down with the engineers and go over the data and said, you guys, you got to quit doing that. You're really screwing up by using up your peroxide. You may need that. You may use it too fast. But of course you don't tell test pilots if they're doing anything wrong or anything dumb with controls, because that's their world. You know, sticks and rudders are their world. So they finally showed us, and that is what prompted the design of the Minneapolis Honeywell 96 flight control system, the blended flight control system, that was developed on the X-15, actually perfected pretty nicely on the X-15, and basically used in tote on the Space Shuttle flight control system for reentry. So that was a direct benefit. But the sweep second hand was started with pressure in the engine, the rocket engine. When the pressure would come up, it would start that sweep second hand, and you use that very diligently for engine shutdown, for energy conditions on shutdown. Let's see, I won't go through the rest of those. Two basic kind of profiles that we flew. A speed or a heating profile where we would be carried out under the B-52. These numbers are not too far off, but they're kind of general, so don't take them as gospel. About probably 170, 180 miles up range for most speed and heating flights. You'd launch at 45,000 feet. Once you were clear from the B-52, then you could go ahead and ignite the engine, fully ignite it. You had a fire going back there, a little pilot light, kind of like lighting a barbecue pit, and it would be burning so that when the propellant came in, it had a fire, it already had a start. So the engine would start up. You'd pull up to about 30-degree climb attitude and climb out and push over at whatever the conditions called for. Whether if it was a dynamic pressure, it might be a little lower altitude. If it was a Mach number that they were designed to study Mach effects, shock waves and things at different altitudes, different Gs, different angles of attack, then you might be a little higher altitude, but around 110,000 feet. And shut the engine down and and glide. I got to get a new thumb. Glide back in to arrive over Edwards Air Force Base at about 35,000 feet. So you could set up the overhead pattern and you'd fly a big spiral, just a big old spiral to line up with the runway. That way you could look and take different energy levels. If you were a little low on energy, you could cut the turn a little tight, keep the turn in tight. If you were high on energy, let it swing wide during this turn and line up and get your energy right to touch down. We repeatedly were able to touch down within 1,000 feet or so of where we wanted to on the dry lake bed. The altitude profiles were carried out a little farther because by the time you lofted over and went ballistic downrange, it took a little more distance from launch to touchdown. So our launch point was farther uprange, still 45,000 feet, 0.8 Mach. Same procedure, get off the hooks, get the engine lit, come up on angle of attack to hold angle of attack until you got the pitch attitude, which was 45 degrees for most of the altitude flights. 45-degree pitch angle, and the engine, your shutdown conditions normally were around 140,000 feet, and then you would glide and coast all over this parabolic arc over the top until you came back down and started picking up enough dynamic pressure to start using the controls again, and then start adjusting your energy to come on in and land. Same thing at Edwards. Now the landing. The landing gear, here's an interesting design thing. The nose wheel they had decided was going to be just a full castering nose gear. It was rubber tires, was pneumatic tires, and they could keep the nose kind of cooled enough to keep the tires from blowing up or burning up. But they didn't want to run hydraulic lines up anywhere they didn't have to. So the nose gear, or all the gear, were free-falling gear, just a hook on a cable that went around pulleys and bell cranks, and you'd pull on the handle, the landing gear handle. You'd actually jerk the hook open, and the gear would fall down. No hydraulics up there, and no nose wheel steering. So it was a free caster nose wheel, and the main gear were back here, way back here at the tail. And the reason for that was, with no nose wheel steering, they figured that they wanted to have the most stability after the airplane was down on its 3-point attitude and sliding out on the lake bed. We landed, most of the flights were at Edwards, and that was 8.5 miles wide. So if you aim for the center, and you touch down, there's no way you're going to make it to the edge anyway, even if the thing had gone off. But you could actually control. If it started to move a little bit, the nose started to drift to the right, you'd put in a left aileron, full left aileron. That would load up the left skid and cause more drag over here, and would kind of drag the nose around. Kind kind of like a dog when it doesn't really want to come to you, and you're calling it. It would kind of give you a little bit of a, yeah, I'll be there in just a minute. You couldn't really avoid anything, but you could keep it. You could think it. It made you think like it was like the little cars in Disney World where the steering wheel really isn't hooked up to anything big. And after 100 knots, it really was the car at Disney World. It didn't have any effect at all. Here's a picture. Here is a good photo that shows the blunt tail. It was a wedge-shaped tail, pointed at the front, came back to a maximum of, gosh, it must have been, 9 or 10 inches wide back there. I don't really remember how wide it was, but that was one of the design features to give it more stability at hypersonic speeds. If we got time, we'll go back and we'll talk about that one a little bit more. There's some other things I wanted to show you. Let me see, what are we talking about? Oh, the landing gear. Now, so this was a good deal on the wake bed for directional stability. But it was not such a good deal for loads on the tail of the airplane, on the main gear of the airplane, because on a conventional airplane, you got the center of gravity ahead of the main gear. You touch down on the runway, the nose kind of wants to fall through, so a pilot will start coming back on the stick, pulling the elevator up, and pushing an air load down on the tail to balance the rate of rotation, so you can control the nose. If you get a good landing on a main gear, then you got most of the works out of the way. Now you got to do is make the nose wheel squeak, and you can walk back, walk into flight ops just strutting like a dog. But on the X-15, it didn't work that way with the gear back there. Stability-wise and protecting skids-wise, moving it back as far as they could, protecting skids from heat. These were steel skids. Protecting them from heat. Moving it back to the back was a good deal. But you can see what happens. When you touch down, the nose is going to start falling through and just slam down harder than heck. And no pilot likes to do that. I mean, that looks like you just quit flying and you gave up and patting yourself on the back already when the flight isn't over yet, and nobody really likes that. So naturally, when you touch down, intuitively you start pulling back on the stick. When the nose starts falling through on you faster than you want, you pull back harder. And sure enough, we were pulling back to where the slab was full, nose, leading edge down, trailing edge up. And of course, what you had was additional air loads back here. The gear was designed with not a lot of margin, but it should have been enough. But if you were heavy for any reason, if you had an engine that quit on you, failed, and you couldn't jettison all your fuel, and you had more weight on board, you had a heavy airplane, you landed a little faster, you had a little more dynamic pressure, the nose fell through, you came back on the stick, you loaded up the main gear, and we were exceeding the limits on the gear. And in fact, on one flight that you'll see in the film, Jack McKay had one of the gear fail on him. He had a bunch of stuff stacked up. The flaps did not come down. He couldn't jettison all his fuel, and he landed fast. And the right gear failed, and you'll see that in the film. And he got out. He lived through this, believe it or not. As the airplane started to roll over, he blew the canopy, which was a good deal because we didn't have really a lot of oxygen. We had about 20 minutes of oxygen, breathing oxygen, after we launched. And that was it. You didn't need any more than that because the flight wouldn't last more than 10, 11 minutes at the most. And everything else was nitrogen for fire suppression. The suit was pressurized with nitrogen. The cockpit was pressurized with nitrogen. So you just had a little bit of oxygen. They would not have gotten up there in time to lift the airplane up off of Jack if he hadn't blown the canopy. So he did that. The thing he hadn't thought about is when he blew the canopy, his head was the first thing that was going to hit and hold the airplane up. And it did fracture some vertebrae, but he got fixed up. So did the airplane, and both of them were flying again, which was a good deal. The leading edge of the wings were solid nickel alloy, and in order to take the heat from the leading edge, where the skin butted up against those, we would get buckling when they had these slots, the expansion slots. Had to cover those things with a little cover. Well, windshield shattering. Oh, this one I got to tell you about. The windows were not all that big. They were maybe that wide and maybe that long. Not a big field of view if you're thinking sitting back and looking out thing. But when the canopy came down, as you'll see, they were right up against your face. And it's just like looking at a baseball game through a knothole in the fence. You get up close enough, you can get a pretty good field of view. So we had a pretty good view out these windows, except for when, with the thermal expansion laws that applied to all these things, steel has a different coefficient of expansion than glass does. And it forms stress points at the corners of the window, and they would shatter like the old car windows used to do, and you leave them out in the parking lot, just glaze over, kind of like you couldn't see out of them. You could kind of roughly tell where the horizon was, but boy, you didn't want to land in with visibility like that. So if the right window glazed over, you'd set up a left-hand pattern and look out the left window. If the left one, you'd set up the pattern to the right. And I've got to tell you, my favorite remembrance of the X-15 was that I really, really wished that I had a flight where both windows would glaze over and you couldn't see out, because they'd vector you back over Edwards, over the lake bed with radar. They could vector you back over and get you over the top. Then you got to blow the canopy so that you could see out to land. And can you imagine coming back? Of course, you were all protected. You had the pressure suit on, you had the visor on, no wind blast, you were strapped in, you weren't going to whip around at all. Can you imagine sliding out after going Mach 6 in an open cockpit airplane? and I honestly, God, I even had a silk scarf. I bought a silk scarf so that before the rescue trucks got up to you on the lake bed, I could wrap that thing around and throw it out over the canopy ledge. But it didn't ever happen. I never got to do that. Now, what I blew it on, also the airplane would expand. At Mach 4.5, I got to really hurry here because we're going to run over a little bit anyway. At about 4.5, about Mach 4, the airplane would start, with heating, the aerodynamic heating would start to expand. It would start to expand and grow. It would grow about 3.5 inches in length, as a matter of fact. And on the sides, there are expansion joints on the airplane, just like bridges have and railroad rails. You know, in the wintertime, there's a gap between them. That's because they shrunk down. And in the summertime, they'll expand out and all these things close up. Well, the X-15 did the same thing, and so they cut expansion joints back here along the fuselage that the airplane would grow. But the gear, as I mentioned before, is a very simple gear. A cable that you grabbed a hold of and pulled, went over pulley, down to bell cranks to the nose gear, back to the gear, to the main gear, and the hooks would let the main gear fall down as well. When they made a modification to the number 2 airplane, they hadn't quite matched up the coefficient of expansion of the cable and the skin, because the cable ran back along, well, I'll show you a little later, along the chines of the airplane next to the cold propellant tanks. So they were cold, and the skin was hot, and the airplane would grow and stretch, and the cable didn't grow and stretch. And did I screw something up? No. Okay. And they and it actually pulled the gear open. So that was a lesson learned slowly, because it took 3 flights to do it. Bob Rushworth had all 3 vents. Nose gear came down on him once, and the scoop came down, and then the main gear. So pilots are so kind to each other. You know, they really love to get gotchas. So we had a placard made, a pretty good sized placard made, to put on the instrument panel every time Bob would go out to fly the airplane, Bob Rushworth. But we didn't have Velcro then, so he couldn't rip it off for the flight. We had to glue it on, so he had to leave that there and watch it. And that was what we had a placard made, reminding him not to extend the gear below. Here's some more heating problems that we had, and I'm really going to hurry up. The shockwave I mentioned, we were carrying a scramjet engine, a prototype of an engine that they wanted to see if they could sustain flame properly, if they could propagate the flame at Mach 8. And they figured the best way to do it, since wind tunnels weren't working too good, was to build an adapter mounted on the bottom of the X-15, mounted on the bottom of the X-15. It's right under here, if you can. I don't know whether you can see that yet or not. But it looked like this. It had a big spike out there on the nose, and the idea was to mount it there, modify the X-15 with more propellant, accelerate on, expand the envelope on out to Mach 8, and check out this scramjet engine. Sounded like a good idea. They coated the airplane with an ablative material to take the extra thermal heat. The thing that wasn't thought out too good was shock effects and shock impingement. And the shock formed on the spike of the engine, laid back across the pylon or the lower ventral fin, and just burned its way through. That was another one of those, well, I guess that's fast enough. We don't need to go any faster than that deals that everybody learned. Entry, real quick. I'm going to really go through this quick. To re-enter the atmosphere from up in space, we did all kinds of maneuvers up there, rolling the airplane to expose the infrared and ultraviolet cameras to the horizon to get signatures, yawing the airplane as you went over the top, and then flying back in. We'd go out at 45 degrees angle, we'd fly back in at 45-degree angle. So and 26 degrees angle of attack was the desired initial angle of attack to arrest the sink rate as you fell back into the atmosphere. So we'd pitch the airplane over to 20 degrees nose low as we started back down. And then as you got into the atmosphere, as you began to pick up dynamic pressure, the nose ball, the cue ball up here, would sense what the angle of attack was and would tell you, and you go ahead and lock on 26 degrees angle of attack, fly that till you've picked up 5 Gs, at 5 Gs or 5.5 Gs, depending on the altitude, hold that till you arrested the sink rate, and then push over before you got level so that you kept coming down and getting into more dense air. Think that, and then start looking out the window. See where the field was, how to set up your energy, whether you needed to S-turn a little bit or stretch it out a little bit, loft up, pull up a little bit and loft and go on in to get into Edwards. But the thing was, it was all out the window. There was no guidance at all. And I think, I'm not going to go through all these. These are a whole bunch of stuff. The two things that really helped directly that we didn't realize at the time were when we got ready to fly the space shuttle, that the low lift to drag ratio, which both airplanes had, were directly applicable to the space shuttle and helped gain confidence with the designers, with the management team really, that it was okay for us to go ahead and fly without adding additional engines on, because the plan was for the initial flights at least, till we really realized whether or not you could land an airplane this big by coming in at a 20-degree dive angle and with no power at all, and the energy bleeds off pretty rapidly. They were going to put a pack of engines in that would live in the payload bay. It would have taken up a third of the volume and most of the weight capability that the space shuttle had. Would have made it very, very ineffective airplane, and it would have really slowed us up a lot. So that was a real benefit to learn that. Here's a couple of comparisons. The X-15 from terminal area energy management is what that T means. That just means you pick it up where you're pitched over and you're doing aerodynamic out the window flight. A little faster in the space shuttle, but not too much. The final approach, pretty close, where you line up, where you're circling around and you finally line up with the runway to get a straight in approach. About the same. Final approach speed, same. Maximum L over D, which is the key, actually was a little better in the space shuttle than in the X-15. And the touchdown speeds were not all that far off. They were different size. I mean, they weren't one-on-one. In fact, the X-15 would fit in the payload bay of the space shuttle. The X-15 was 50 feet long, and the space shuttle had a payload bay 60 feet long. Wingspan was a little too big, but as Jeannie reminds me, you could do the Navy trick and fold the wings up and get it in there if you had to. That's it. And let me tell you, we'll run over. If anybody needs to leave now, please do. It'll take Dave for a minute to get up here to tell everybody thank you and do all his thing. So while he's doing that, let me quick say, is there any? Let's take a couple of questions while he's coming up here, and would anybody like to ask anything? Anybody got anything? Well, good. You were really paying attention. I don't see any hands. Hurry up, Dave. Oh, here, wait a minute. We got a couple. Go ahead, sir. Yeah.
With the X-1, it did not have swept wings, and the Germans had developed the swept wing technology during World War II. Had it not filtered over into the U.S. yet?
The question was, the X-1 had straight wing rather than swept wing design, and essentially, why didn't we take advantage of what the Germans started learning about swept wing design? I don't know the answer to that. I just don't know. I think they were so interested in finding out the airflow over a conventional wing, because we were still going to build fighters with conventional wings at that time. I just don't know the reason why, though. That's a good question. We have to go back to the people that were design team at that time, and if there's any of them left. And yeah, and right behind you there, yeah.
Bill, this is kind of off topic. Growing up, I was always told stories about one of your flight instructors, Henry.
Henry Dittmer, absolutely, you betcha.
He got a Stitch flutterbug from his house to the airport the day before inspection.
Did he really?
Well, that's what I
Well, the question was, Henry Dittmer was the guy that taught me to fly at Cessna down there. He was the head of the power plants division at Cessna, and he knew that I really wanted to learn to fly. So he had a CFI and he taught me to fly, but he made me work at Rodden Airport. I was sweeping hangars and cleaning out toilets, and 8 hours of toilet cleaning for 1 hour in a Cessna 120. Boy, that's a fair trade. Yeah, Henry decided we needed an airplane and we needed an experimental airplane. So he ordered a Stitch flutterbug. Is anybody familiar with what a Stitch flutterbug looks like? They're ugly. They're one chord. I mean, the chord is the same from the root to the tip, and it's a tricycle geared airplane. 3 wheelbarrow wheels is what it had on it, and it mid-wing. It had a 65 horse engine. We built it all over Henry's house. The kitchen was the engine room where we rebuilt the engine. The living room had the wings in it. No, the garage had the fuselage. The living room had the wings, and the tail surfaces were in the spare bedroom upstairs. When you dope them and dry them out, boy, the house really smelled. But we got it put together, ran the engine up, and the FAA, wouldn't let us fly it right there off the field, right next to Cessna, or even out at Rodden's. Had to take it out to an old auxiliary airfield about 8 miles out of town, and so we would crank it up to run the engine, tie a rope around the tail and tie it to a tree and let the engine run in a little bit. And one day we were out doing that. We were about ready to fly it, and Henry said, "Why don't you go get some hamburgers and a malt and meet me out at the airport out where we're going to fly this thing?" And I said, "Okay." I didn't know what he wanted to do. He was going out there with his car to look it over and check it out. While I was gone getting the hamburgers, he flew the airplane out to where the first flight was going to take place. So not a real gross thing, but Henry was a tremendous pilot and a tremendous instructor. He taught me not only how to fly, he taught me an appreciation of airplanes and aviation.